the origin of the universe is a mystery that has puzzled scientists and philosophers for centuries. It is not currently understood how the universe could have arisen from nothing, as the concept of nothingness is difficult to define and understand. It can be challenging to comprehend the concept that there may not have been anything before the Big Bang. Some people compare this idea to asking what is north of the North Pole, as there is no answer because there is no such thing as north of the North Pole. Similarly, it may be difficult to understand how everything we see and even that which is beyond our visibility once existed within an infinitesimally small point, surrounded by emptiness.
I'm happy to say when I don't have an answer to something. I don't know. The proper question would be what started it? Because who implies that there's some kind of human entity, but I don't know. If I don't know, I'm going to say I don't know. There are people, though, among us who, when they don't know something, they still have to have an answer. Think of the people who spot UFOs in the sky. There's some light moving in a way they don't understand, so it's an unidentified flying object. But listen to what they do next. They say, wow, I don't know what I'm looking at. It must therefore be intelligent aliens visiting us from outer space. You have not justified that you now know what it is after you just said you don't know what it is. So if I don't know how the universe got here, I'm not going to then assert that I know. I'm going to say, I don't know, we got top people working on it.
According to the Big Bang theory, the universe began as a singularity, a point of infinite density and temperature. At this time, the universe was thought to be filled with a vast amount of energy and no matter. The singularity is thought to have expanded rapidly, and cooled as it expanded. As the universe cooled, the energy present in the early universe was converted into matter and antimatter, which eventually combined to form the first atoms. With our current understanding of the origin of the universe, scientists were able to put different timelines of what happened during the Big Bang into different epochs. The first was the Planck epoch. This was the very first epoch of the universe, lasting from 10 to minus 43 seconds to 10 to minus 36 seconds after the Big Bang. During this time, the universe was incredibly hot and dense, and the fundamental forces of nature were not yet distinct. The Grand Unification epoch. This epoch lasted from 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang. During this time, the temperature of the universe cooled enough for the fundamental forces of nature to become distinct. The Inflationary epoch. This epoch lasted from 10 to the minus 32 seconds to 10 to the minus 12 seconds after the Big Bang. During this time, the universe underwent a rapid period of expansion, known as inflation. This expansion smoothed out the universe and set the stage for the formation of the first structures. The Electroweak epoch. This epoch lasted from 10 to the minus 12 seconds to 10 to the minus 6 seconds after the Big Bang. During this time, the temperature of the universe cooled enough for the electroweak force to break into the electromagnetic force and the weak nuclear force. The quark-gluon plasma epoch. This epoch lasted from 10 to the minus 6 seconds to 10 to the minus 4 seconds after the Big Bang. During this time, the universe was filled with a hot, dense plasma of quarks and gluons, which would eventually cool and combine to form protons and neutrons. The Hadron epoch. This epoch lasted from 10 to the minus 4 seconds to 10 to the minus 2 seconds after the Big Bang. During this time, the universe cooled enough for quarks and gluons to combine and form hadrons, such as protons and neutrons. The Lepton epoch. This epoch lasted from 10 to the minus 2 seconds to 1 second after the Big Bang. During this time, the temperature of the universe cooled enough for leptons, such as electrons, to appear. The Photon epoch. This epoch lasted from 1 second to 380,000 years after the Big Bang. During this time, the universe was filled with a hot, dense plasma of protons, neutrons, and electrons, which would eventually cool and combine to form atoms. Singularities are fascinating because they represent a point where the fundamental laws of gravity are in the universe. However, Einstein's general relativity breaks down and becomes mathematical nonsense. Relativity, remember, it is the theory that describes space and time. But at singularities, not only do the spatial dimensions disappear, but so does time. Essentially, asking questions about what came before a singularity is comparable to asking about one's location without the concept of space. In both cases, the question becomes meaningless. Paul Davies argues that there was no before the Big Bang because the Big Bang marks the beginning of time. However, our recent Detailed observations of fluctuations in the cosmic microwave background radiation, which is a remnant of the Big Bang, have revealed that this assumption of a singularity might be incorrect. This means that the Big Bang is no longer thought to be the beginning of time. The concept of the Big Bang is supported by a number of observations, such as the expansion of the universe and the abundance of light elements. However, the Big Bang theory does not provide a complete explanation for the origin of the universe, and it is not currently understood what caused the singularity to exist or what triggered the expansion of the universe. There are a number of theories that have been proposed to explain the origin of the universe, such as the idea of quantum fluctuation, the concept of a multiverse, or the theory of cosmic inflation. However, these theories are still being researched and tested, and it is not yet clear which, if any, of these ideas will be able to provide a complete explanation for the origin of the universe. The idea of quantum fluctuations has been proposed as a possible explanation for the origin of the universe. According to this idea, the universe could have arisen from a quantum fluctuation in the vacuum of empty space, which led to the creation of matter and energy. This theory is known as the quantum fluctuation model of the universe. A quantum fluctuation is a temporary change in the amount of energy at a point in space. It is a fundamental prediction of quantum mechanics, which is the theory that describes the behavior of matter and energy on the smallest scales. According to quantum mechanics, particles can exhibit both wave-like and particle-like behavior, and the behavior of a particle can be described using a wave function. The wave function of a particle describes the probability of finding the particle at a particular location in space. Quantum mechanics also predicts that particles can be created and destroyed in pairs. A process is known as pair production. For example, an electron and a positron, which is the antimatter counterpart of the electron, can be created from a single photon of light. This process is described by the equation E equals mc squared, which shows that energy and mass are interchangeable and that matter can be created from energy. A quantum fluctuation is thought to be a temporary change in the amount of energy at a point in space due to the uncertainty principle, which states that it is impossible to know both the position and momentum of a particle with complete precision. According to the uncertainty principle, the uncertainty in the position of a particle is inversely proportional to the uncertainty in its momentum. This means that the more accurately we know the position of a particle, the less accurately we know its momentum, and vice versa. As a result of the uncertainty principle, the energy of a particle can fluctuate temporarily, as the uncertainty in the position of the particle leads to an uncertainty in its energy. These fluctuations can result in the temporary creation of particles and antiparticles, which can then annihilate each other and return to the original state of energy. However, the quantum fluctuation model of the universe is still a subject of research and debate, and it is not yet clear whether this idea is a viable explanation for the origin of the universe. Perhaps, according to cosmic inflation, one of the leading theories of the universe's pre-Big Bang origins. It really did come from nothing. This requires a little bit of an explanation, and is what is most frequently meant by a universe from nothing. When we imagine the earliest stages of the hot Big Bang, we have to think of something incredibly hot, dense, high energy, and almost perfectly uniform. When we ask, how did this arise, we typically have two options. It's with the universe that must have been born this way. The universe was born with these properties, which we call initial conditions, and there's no further explanation. Or we can do what theoretical physicists do best, develop theoretical explanations for the conditions that existed at the beginning of the universe, teasing out concrete predictions that differ from the standard, prevailing theory's predictions, and then going out seeking to measure the critical parameters. Cosmic inflation came about as a result of taking that second approach, and it literally changed our conception of how our universe came to be. According to the theory of inflation, the hot and dense conditions that existed at the beginning of the universe may not have been the result of a singularity with infinite heat and density. Instead, it is possible that the hot Big Bang was preceded by a period of extremely high energy density in the fabric of space, which caused the universe to expand at a rapid rate, inflation. When this inflationary period ended, the energy was converted into matter, antimatter, and radiation, resulting in the hot Big Bang that we observe. In this way, the hot Big Bang can be understood as the aftermath of inflation. The theory of inflation provides a detailed explanation for the observed features of the universe, such as its uniform temperature, flat spatial geometry, and lack of evidence for a grand unified epoch. It also makes specific predictions about the type and spectrum of density fluctuations that should exist, which have been confirmed through observations. According to this theory, the structure and complexity of the observable universe we see today can be explained by the natural process of energy transformation occurring within empty space, which is filled with a large amount of field energy. That's the big idea of getting a universe from nothing, but it isn't satisfying to everyone. For many people, the idea of nothingness is difficult to reconcile with the existence of the universe, including space and time, the laws of physics, fundamental constants, and the non-zero field energy inherent to the fabric of space itself. It is possible to conceptualize a location outside of space, a moment beyond time, or conditions without physical reality, but from a physics perspective, it is difficult to make sense of the concept of absolute nothingness. How can space and time emerge from a state of non-existence, or how can space-time emerge at a specific location or time without a definition of location or time? It is also unclear where the rules governing quanta, such as fields and particles, come from in the absence of physical reality. Unfortunately for us all, inflation, by its very nature, erases any information that might be imprinted from a pre-existing state in our observable universe. Despite the limitless nature of our imaginations, we can only draw conclusions about matters for which tests involving our physical reality can be constructed. No matter how logically sound any other consideration may be, including a notion of absolute nothingness, it's merely a construct of our minds. The theory of cosmic inflation is supported by a number of observations, such as the cosmic microwave background radiation, the expansion of the universe, and the abundance of light elements. However, the theory of cosmic inflation is still being researched and refined, and it is not yet known if it is a complete explanation for the origin and evolution of the universe. Our whole lives we have been taught that you can't get something out of nothing. The question of how the universe and all its components, such as life, planets, stars, and galaxies, could have emerged from absolute nothingness remains largely unanswered. However, as we improve our understanding of quantum mechanics, theoretical physics, astrophysics, and cosmology, we are gaining clues about the physical processes that may have been involved. For example, it has been observed that particles can pop in and out of existence, appearing and disappearing spontaneously. Nobody knows exactly how all the matter, antimatter, dark matter, energy, and dark energy were contained in a singularity not much larger than a Planck length in diameter. Nobody even knows what dark energy really is. But the evidence is there that the Big Bang happened 13.7 billion years ago, from several different sources. The universe is expanding, indicating a starting point. And space is exactly the temperature one would expect in a universe that was created in a hot Big Bang. Given the evidence that the Big Bang occurred, it follows that a singularity must have existed as well. This leaves us with two possibilities: the singularity emerged on its own, or it has always existed. But there are no clear answers based on evidence either. It is unclear if we will ever fully understand what caused the Big Bang and the events that led to the universe we know today. However, many people, myself included, will continue to ask these questions and seek answers through exploration and research. We may never know, but we will make progress. But there are some theories that our universe is inside a supermassive black hole, which is very much terrifying. To find out more about this theory, click the video on your screen. Thanks for watching and subscribe for future videos.